Hello. Today we'll discuss about another important function in Laplace transforms, that is the delta function or shocks. Okay. So let me introduce the delta function. So Dirac delta. This is delta of t minus a. Informally, delta of t minus a is infinity if t equals to a, 0 if t is not a, and integral from 0 to infinity delta of t minus a times f of t dt equals to f of a, no matter which smooth test function we pick here, f of t. So it's very important to make a so this is not so it is not makes sense intuitively, but we want to make a formal sense of this. So we have to make a formal sense of the delta function by connecting it with some rectangles. So connection with rectangles and making sense of delta functions. Connection with rectangular signals and making sense of delta of t minus a. So technically, delta of t minus a is not technically a function; it's a distribution. So it's like imagine like a box. In this box is delta of t minus a. Input a test function f of t, and once we provide this input f of t, this machine spits out the output f of a. But such like we define it exactly in this way, like an algorithm. Input is f of t, output is f of a. This cannot be done by a function. So we want to find functional approximation of the delta functions. Okay. So the best approximation are rectangles. Okay. So we are looking at rectangles. The rectangular signal between a and a plus epsilon. Epsilon is a small positive number. So a rectangle which is thin and tall, the width of the rectangle is epsilon, and the height of the rectangle is 1 over epsilon. So this is a rectangle. So what's the picture for this rectangle? Between a and a plus epsilon, the rectangle takes the height 1 over epsilon. So how can we formally define this rectangle? Prior to a is 0. Between a and a plus epsilon is 1 over epsilon. And from a plus epsilon to infinity is again 0. So let me use a color for this one. 0 before a, 1 over epsilon from a to a plus epsilon, and 0 after a plus epsilon. So this is a rectangular signal. So when epsilon approaches 0, we get better and better approximation of the delta function. So when epsilon approaches 0 plus, then R, the rectangular signal from a to a plus epsilon, and height 1 over epsilon or t, gets closer and closer with delta of t minus a. Okay, so let's try to prove this stuff, right? So let's try to keep this rectangle here for a while and try to use this rectangle against a test function. So what will be integral from 0 to infinity of the product in the rectangle rectangular signal between A and A plus epsilon and height 1 over epsilon of t, and the test function f of t dt. Because when epsilon approaches 0 plus, these rectangular signals, if they become thinner and thinner at the same time, taller and taller. Thinner and thinner, thinner, taller and taller, and so on. So when epsilon approaches 0 plus, this series of rectangles, thinner and thinner, taller and taller, but preserving the area 1. So in this case, area is 1. So there's a preserved constant in this evolution. When epsilon approaches 0 plus, this approaches delta of t minus a. How to prove this? By using this integral. Integral from 0 to infinity, the rectangular signal from h to a plus epsilon, height 1 over epsilon, multiplied by a function f of t dt, there's a test function. Let's see what we get. We are really, because we want epsilon to approach 0 plus, we are really interested in limit when epsilon approaches 0 plus. So limit when epsilon approaches 0 plus, integral from 0 to infinity, the rectangular signal from a to a plus epsilon, height 1 over epsilon, which means we preserve always the area is 1. So the width of the rectangle is epsilon, the height is 1 over epsilon, which makes the area 1, times f of t dt. So this integral, when epsilon approaches 0 plus, we want to be exactly like the delta function, which, so compared to our idea that integral from 0 to infinity delta of t minus a and the test function f of t dt equals to f of a. So you want to get the same effect here as here. So we want this limit to be f of a. So how come? Okay, so this will be the integral is from 0 to infinity, but this rectangle is only matters from a to a plus epsilon because otherwise it's 0. So the integral from 0 to infinity actually is an integral from a to a plus epsilon. Integral from a plus epsilon. The rectangle between a and a plus epsilon is 1 over epsilon. 1 over epsilon being a constant, put the constant in front. 1 over epsilon. Okay, so the rectangle got 1 over epsilon. The constant is taken out in front of the integral. Then we are left with f of t dt. And that's a L'Hopital form. So this will be the limit. Okay, we have to still to keep limit when epsilon approaches 0 plus. 1 over epsilon. Integral from a to a plus epsilon f of t dt. So limit when epsilon approaches 0 plus. The numerator, integral from a to a plus epsilon f of t dt divided by epsilon. What kind of integral is this one? F of t again is a smooth continuous function, right? So all the desirable properties we want. So this, when epsilon approaches 0, it's a 0 over 0 type. So this will be a 0 over 0 type. We apply L'Hopital. So that's the same way. Let me continue here. Limit when epsilon approaches 0 plus, or doesn't matter at this moment. Limit epsilon approaches 0. The derivative of the integral is f of a plus epsilon over the derivative of the denominator is 1, right? And because the function is assumed to be continuous, equals to f of a as expected. So we want to produce the same effect for the integral from 0 to infinity. Delta of t minus a of dt gives the same effect as the limit on epsilon approaches 0 plus the integral from 0 to infinity of those thin and tall rectangles. Thin and tall rectangles with area 1. So the thinner and the taller they get, the closest approximation of the delta function. So that's very important. So what we have to know at this moment, this is the most important formula. Integral from 0 to infinity, delta of t minus a for t dt is f of a, and introduced by this approximation with rectangles. Now let's try to find the Laplace transform of delta function. Laplace transform of delta of t minus a. Delta of t minus a is shock. It is applied to the system when t equals to a. That's the intuitive meaning. Shock applied at t equals to a. So even more, if you want, so technically shock of intensity 1 correlates the area of those thin and tall rectangles are all the areas are always 1. If you want a shock of intensity 2, so we have to use thin and tall rectangles of area 2, right? So this is a shock of intensity 1, if you want. Apply at t equals to a. That's the meaning of delta function. A shock applied to the system, right? So let's see now how does it? It's a very nice Laplace transforms and very strong application in differential equations. So there's the Laplace transform. Integral from 0 to infinity, e to the minus ht, delta of t minus a dt. What is this? Now let's use this formula. Integral from 0 to infinity, delta of t minus a f of t dt. So whenever you input in the system f of t, outcome of the machine delta of t minus a, f of a. Input f of t, output f of a. So in here is input e to the minus st, output e to the power minus sa. So or they put like we consider the formula e to the power minus as is the Laplace transform of delta function. Compared to the Laplace transform of the unit step function, which would be e to the minus as over s. So compared to Laplace transform of u of t minus a equals to e to the minus as over s. So very important, Laplace transform of delta function at a. So delta function applied to the system at a. So shock applied to the system at a is e to the minus as. With this idea in mind, let's try to start solving initial value problems involving delta functions. So essentially, these are oscillators. So Laplace transform of delta function is e to the minus as. So let's keep this in mind. So at this moment, let's start for some applications. Let me recall the Laplace transform of delta of t minus a equals to e to the minus as. Again, delta of t minus a is a shock applied to the system at t equals to a. So in what follows, let's do some exercise. Exercise 1. All of them are initial value problems. X second plus x, this is our standard oscillator, equals to, we apply delta function right away, delta of t, as in delta of t minus 0. Right? So so delta of t. And then let's for simplicity put both initial conditions 0. So x of 0 equals to x prime of 0. That's the first initial value problem we do here with delta functions. So what is this one? X second plus x. X second plus will be our oscillator. What is delta of t? Delta of t, what's the right hand side? Is the external input. External input or influence. So basically, what do we do here? We have an oscillator. We keep this oscillator at the moment 0 with a shock of intensity 1. Keep the oscillator at t equals to 0 with a shock of intensity 1. Okay, so let's see. Solve it a standard way to do initial value problems. Say small x of t transforms into big X of s, small x prime into sx, small x second into s squared x, and delta of t, what do we transform? know that delta of t minus a is e to the minus s, delta of t minus 0, e to the minus 0s, which will be 1. So the Laplace transform of delta of t, the delta function at 0, so shock applied to the moment t equals to 0 is 1. Okay, with this, it's like a dictionary and transform the t space to the s space. X second becomes s squared x. Small x becomes big X. Equals to delta of t becomes 1. Right? So big X times s squared plus 1 equals to 1. Big X equals to 1 over s squared plus 1. Okay, this is the solution of the differential equation encrypted. Encrypted is just the Laplace transform. To decrypt it, just take the inverse transform. So once we got capital X is 1 over s squared plus 1, small x of t will be the inverse transform of 1 over s squared plus 1. And we are already familiar with this one, with the sinus of t, which is very intuitive. So we have an oscillator and kick this oscillator at the moment 0, apply heat, and then it begins to oscillate like a sinus. So shock at the moment 0, I have to put here this shock at the moment 0. So delta of t is a shock at t equals to 0. Shock of intensity 1 at t equals to 0. So apply this shock to the oscillator, hit it, and then also starts to oscillate like a sinus. So t equals to something, and it will continue to oscillate forever once you apply the shock at the moment 0. Okay, now let's try to do more and more sophisticated problems. This is the easy one. Let's imagine that exercise 2. The shock is applied a little bit later. So x second plus x equals to delta of, let me make it t minus pi. X of 0 equals to 0. X prime of 0 equals to 1. Okay, so let's solve this initial period problem. Solution. So exercise 2 here. Solution. Small x of t again transforms into big X of s. Small x prime, because of the initial condition, small x of 0 is 0, transforms into sx. Small x second transforms into multiplied by s squared x minus 1 next initial condition. And delta of t minus pi transforms into e to the minus pi s. And there's a dictionary, and apply the dictionary to this IVP and transform it to an S equation, algebraic equation. So we get x second is s squared x minus 1, right, this x second, plus big X equals to e to the power minus pi s. Okay, let's keep the x on the left, non-x is to the right. So s squared plus 1 times x equals to 1 plus e to the minus pi s. So x, capital X will be 1 over s squared plus 1 plus e to the minus pi s times 1 over s squared plus 1. Let's start to find out the inverse transform of big X. So there's our solution, the solution of differential equation encrypted. So the encrypted way to find the inverse transform. Okay, so let's see what we get here. This one, if we decrypt it, the decryption will be, the inverse transform of this one will be sine t. And this one, be careful, we have a delay here, right? So in itself, this would be sine t. But because of e to the minus pi s in front of it, this whole product, e to the minus pi s times 1 over s squared plus 1 is u of t minus pi times sinus of quantity t minus pi. So let me write down like a trick on a scrap paper, trick stuff. Sinus of t minus pi is sine t cos pi minus cos t sine pi. From trigonometry, sine t cos pi minus cos t sine pi. Sine pi is 0, so this is 0. Cos pi is minus 1. So this will be finally minus sine t. Okay, so after all, we got a small x of t equals to sine t plus u of t minus pi times minus sine t. So minus u of t minus pi sine t. We circle this one, so we have to treasure the valuable information we got so far. Now let's do the chart, like we did yesterday. I want to keep this exercise. So this x of t. Okay, after doing some algebra, this is the x of t. So let's do the chart. Everything starts at 0. Between 0 and pi, we get sine t. So this jump didn't happen yet. So u of t minus pi is unit step function. 0 before pi and 1 after pi. So before pi, nothing happened. So just sine t. After pi is sine t minus 1 sine t. So sine t minus sine t is 0. Sine t minus sine t, because the sine t here minus 1 sine t is 0. So sine t before pi and 0 after pi. Being 0, the output is 0. So what's the solution of this initial value problem in a graphical form? Before pi is sine t, and after pi is 0. How do you explain this by using our idea of a shock for the delta function? Okay, so by using the initial value problem, the initial conditions, this oscillator starts as a sinus. Starts as a sine function. Because sinus at 0 is 0, and the derivative of the sinus at 0 is 1. So the base of solution for the linear homogeneous constant coefficients equation x second plus x equals to 0 is constant sine t. So every solution of x second plus x equals to 0 is a combination of constant sine t. Now, if x of 0 is 0 and x prime of 0 equals to 1, that's a sinus, right? So this starts as a sinus. Right? So normally it would be like a sinus forever, right? But at the moment pi, we have a shock. So this shock at the moment pi. So let's see what happens to oscillator. Oscillator moves in the negative direction. Exactly this moment meets with a shock of equal intensity, and it will annihilate. So once oscillator goes this way and meets with a shock going in a positive direction, oscillator moves in the negative direction, meets a shock in the positive direction, so it kind of goes flat because of this shock. And this explains the solution we already know, right? The reason for this solution. Okay, so let's do other ones. Exercise 3. Exercise 3 will involve some non-trivial amplitudes. Exercise 3. Okay, so let's exercise 3. So I got here. X second plus x equals to 3 times delta of t minus 5 pi over 2. What we got here? At the moment 5 pi over 2, the system receives a shock of intensity 3 because the 3 delta functions. 5 pi over 2. So at the moment 5 pi over 2, the system receives a shock of intensity 3 because there are 3 delta functions. And then let's make initial conditions. X of 0 is 0, x prime of 0 equals to 1. Okay. As always, here's a solution. Small x of t transformed into big X of s. Small x prime into s big X because of the first initial condition. Small x second into s squared x minus 1 because the second initial condition. And delta of t minus 5 pi over 2, t minus 5 pi over 2, with the shock applied the system of 5 pi over 2 transforms into e to the power minus 5 pi over 2s. Okay, this is a dictionary which you use to convert the differential equation to an algebraic equation. X second plus x, so s squared x minus 1 plus x equals to 3 e to the power minus 5 pi over 2s. Again, x to the left, non-x to the right, so x times s squared plus 1 equals to 1 plus 3 e to the minus 5 pi over 2s. Divide by s squared plus 1 and get a clean x. Big X will be 1 over s squared plus 1 plus 3 e to the power minus 5 pi over 2s, and again 1 over s squared plus 1. That's the solution of differential equation, but encrypted. So we have to decrypt it. So convert to a T space. Converting a T space amounts to an inverse Laplace transform. So Laplace transform goes from T space to S space, inverse transform goes from S space to T space. So this one goes to sine T, transforms back into sine T, and plus, put 3 because of the linearity, I have to put a 3 here. In itself, this will go into sine T. But of this exponential before we have a delay. So the whole of this stuff goes into u of t minus 5 pi over 2 unit step function. Sinus of quantity t minus 5 pi over 2. And then we get here on the script paper some trig formula. What will be sinus of t minus 5 pi over 2 equals to sine t cos 5 pi over 2 minus cos t sinus of 5 pi over 2 equals to cos 5 pi over 2 is 0, so that's 0. Sinus of 5 pi over 2 is sinus of 2 pi and a pi over 2, which is 1. So eventually get minus cos t. So sinus of quantity t minus 5 pi over 2 is minus cos t from trigonometry. So let me write down again. So small x of t. Let me try to elaborate on this. Is sine t. Sinus of t minus 5 pi over 2 is minus cos t. As we discussed before, minus cos t. So what we got here? Sine t minus 3 u of t minus 5 pi over 2 cos t. So sinus of t minus 5 pi over 2 is minus cos t. So minus 3 u of t minus 5 pi over 2 times cos t. So circle this one, and next with the chart. Okay. Chart of the solution. That's a 0. That's 5 pi over 2. So we got here a jump from 0 to 1 unit step function, but 5 pi over 2. So this function, unit step function of t minus 5 pi over 2, jumps from 0 before pi over 2 to 1 after 5 pi over 2. So we got 0 before pi over 2. So here is sine t, because no jump happened yet. After the moment of the jump, we get sine t minus 3 cos t. And then, so sine t if t is smaller than 5 pi over 2, and sine t minus 3 cos t if t is greater than 5 pi over 2. For this, the last formula here, we want to find the amplitude for this oscillation after 5 pi over 2. So amplitude will be square root of the sum of the squares of the coefficient of sine and cosine. So 1 plus 9 will be square root of 10. So the as a result of this shock applied at 5 pi/2 to the system, the amplitude of the oscillator increased from 1 to square root of 10. And the energy of the oscillator, because it's proportional to the square of the amplitude, increased by a factor of 10. Right? So it's a very strong increase of the energy of the oscillator. Okay, so basic stuff. So we did some basic stuff about using delta function in Laplace transforms, and more about it in homework to be assigned shortly. So I'll see you tomorrow then.